This is the Chapter 5, Functional Groups, Acids and Esters, Slides, Part 2, additional commentary. So, in this commentary we're going to explore the reverse of traditional esterification. And we call this ester hydrolysis. It's a reverse of esterification, forming alcohols and acids with a loss of water molecule. So, to put it into perspective, if we went back to our ISIS sketch program, and if we take a look at a traditional esterification, we learned that if on the left-hand side we had our starting reactants, an ester and an alcohol, a acid and an alcohol, it's going to form a brand new ester and a new water. Now, notice how the reaction can go both ways. So if we wanted to, we can go ahead and swap places. And we can bring these products over on the left-hand side and bring the starting reactants to the right-hand side, as those would be the newly generated products. So, assuming we're starting off with assume we're starting off with our ester and water with the acid catalyst, and this time is our starting reactant. So I'm going to go ahead and scroll down here. We have what's called ester hydrolysis, and we're going to start off with these as reactants in an acid catalyst. The water and the ester are going to react, forming an acid and an alcohol. So in this case, the bond would break, and the incoming water molecule would be used up, forming a hydrogen on the original alcohol, and then a additional alcohol on the carbonyl group, forming the original acid. Oops. Provided it stays as an acid. Let's see. Okay, let me go ahead and change this. There we go. So now, having our products as our starting reactants, we can go ahead and create a acid and a alcohol. Now, we have the same dilemma as we did in the traditional esterification. This is a reversible reaction. So as soon as we used water to cut apart, aka hydrolyze, the ester, forming the acid and the alcohol, there's no reason that the acid and alcohol at a later time just can't sit there, or there's no reason they can't just come back together again, forming the original ester that we started off with. So, we need another type of reaction called a carboxylic acid salt product formation. And we've covered this in Chapter 5, Part 1. Instead of a starting acid, we're going to use a sodium hydroxide as a base to create a salt product of a starting ester. And whenever we use a base to break apart a ester, we call this saponification. Consequently, it will go ahead and create a new carboxylic acid salt product. So in this case, it's going to go ahead and break apart. and we'll go ahead and we'll have a carboxylic acid salt. So let me go ahead and change this molecule. It's going to have a excess negative charge, and then you have a nearby sodium, and its opposite charges are going to balance out. You then have a leftover water molecule. Notice the original sodium hydroxide is used up, where the hydrogen and oxygen were used in making the final alcohol. Now, if we go to the slides really quick, here is the ester hydrolysis that we talked about. Notice it's reversible. And let's go to the saponification. In this case, notice this is why we like using our base, because it makes a permanent salt product. We've permanently broken up the ester, forming a salt product. Unlike the hydrolysis, where it's a reversible reaction, just as soon as we created the product, it can go back and form the original reactant. In this case, the original reactant is an ester. So going to our slides, watch how I get rid of that reversible red arrow right here. And it completely forms our products with no reversible reactions. I think I beat that to death. Let's go ahead and go back to the slides, and I'll go through the slide examples in detail. Here is ester hydrolysis. Again, we use water to break apart the ester. And the hydrogen is going to go ahead and combine with the carboxylic acid ester, and it's going to combine with this portion of the ester, forming a ether. The leftover hydroxide from the water is going to go ahead and combine with the ester, forming an acid. Again, ester hydrolysis is a reversible reaction, so as soon as these products are formed, there's no reason it can't go in the opposite direction, just as a traditional esterification would. Let's go down to this example right here. Here we have a hydrogen, and it's going to go ahead and combine with this portion, forming a alcohol, and then we have the remaining hydroxide from the water combining with the leftover carbonyl portion, forming our acid. So you'll be responsible for predicting the products as well as naming the UPAC version of the UPAC name of the products. These are all common names, by the way: acetic acid, ethyl alcohol. I could ask you to name the UPAC version, in which case this would be ethanoic acid, and this one over here would be 1-ethanol. So here's another example down here. I like this example down here. That's pretty cool. Let's go to the next one. Saponification. This is a non-reversible reaction, aka irreversible reaction. Notice it goes one direction, and it forms a product. The product never reverses, forming the reactant. It only forms a product. So here we have a starting ester. I'm going to erase all this stuff. Here we have a starting ester. The R portion connected to the single bonded oxygen. The R portion is going to combine with OH from sodium hydroxide, forming the alcohol. The leftover ester is going to combine with the sodium, forming the carboxylic acid salt. Here's a nice example of one: methyl benzoate. CH3 combines with the OH, forming this is the common name, methyl alcohol. The UPAC name would be 1-methanol. The leftover methyl benzoate is right here where the oxygen combines with the sodium and it creates a salt product, sodium benzoate. Notice this is an ionic bond. Also notice we started off with a ester and now it formed a ionic bond. So, as far as polarity goes, one of the reasons we would undergo, or we would have a molecule undergo saponification, is to change its polarity. For example, here I have a ester. In this case, as a pure substance. Oops, So PS, pure substance. As a pure substance, it's going to be dipole-dipole. If it were a mixture with water, then it would be hydrogen bond. Compare that to the saponified product, the salt formed product. In this case, this is going to be ionic. So it'll be ionic in both PS for pure substance as well as a mixture with water. So we've increased the polarity of this portion right here, which makes it a lot more soluble in water. On a side note, acid chlorides, just like esters, it's going to be, for a pure substance, PS, it's going to be dipole-dipole. And then if you were to sit there and mix it up with water, then this portion right here that I'm highlighting with my yellow pen, this portion right here is going to go ahead and hydrogen bond if it was mixed with water. So, as you can tell, sodium benzoate is the most polar of all of these molecules we just talked about because of the ionic bond here, creating the ionic forces. Thereby it has the highest polarity and is most likely to dissolve in water. So, in this example right here, it's an ugly example, and I will actually give you future slides. I have given you future slides with better examples. But just to start off with, this right here is a triglyceride, where here you have a glycerol head with 3 fatty acid tails, carboxylic acid tails, long non-polar tails. You add in sodium hydroxide, and the sodium hydroxide is going to cause a saponified reaction. The sodium then combines with each of the fatty acid tails, creating a acid salt, and then a leftover glycerin molecule. Looks like Mickey Mouse. And then you have, and I'll let the animation go through one more. So we add in the sodium hydroxide, and then the esters form acid salts. So even though we call them fatty acids, it was actually part of an ester with this 3-pronged glycerol molecule. So I feel like I'm trying to catch up with this animation. Let's go ahead and go to the next slide. So in this case, they were originally esters. After we did a saponified reaction, we now have acid salts. Consequently, this side over here is extremely polar. this side over here, these long tails, are extremely nonpolar. Consequently, this side over here is really good at sticking to dirt, oil, and other nonpolar substances, whereas this side over here is really good with sticking and dissolving in water. So, as you've just figured out, obviously, saponification is named after the process of making soap. So now you understand how to make soap. You can make and you can sell soap. I digress. All right. Let me go ahead and open this back up. Let's go ahead and finish up these slides. So in this case right here we have phosphoric acid. This right here is an example of an acid which has no carbon. It's phosphate. So therefore it's an inorganic acid. As I said before, this would be an example of a biomolecule if it's found in the body, which, let's see, phosphoric acid, no, actually it's not. It's actually, the phosphate is actually found. But phosphoric acid by itself is, well, actually, depending where it starts from in the body, it's, alright, don't worry about it. We're getting into little things you do not need to worry about, and I can argue with myself all day long. Yeah, let's move on. Here we have phosphoric acid. It's inorganic because there's no carbon present. The phosphoric acid, if it's nearby a water molecule, can undergo inorganic esterification, where the hydroxyl group and the hydrogen will come together forming water, and then the leftover oxygen will combine with the phosphate, forming a phosphate ester. Notice in this phosphoric acid it has 3 alcohol groups. So if we have it has 3 OH groups that make up the phosphoric acid. So if we combine it with 3 alcohols, then we can have 3 esters form, similar to the previous molecule where we started off with a triglyceride, as they call it. So in this case, notice the number 3. So if I have 3 of these alcohols, 1, 2, 3, and then it will form this structure right here. I do not have a arrow here. You may have to put in your own arrow. So this is the reaction arrow, and then this is the after. If I test you on this reaction, it'll only be on this particular one right here. I'll just copy and paste it on a future quiz test. I'm not going to test you on the naming schemes. Simply be able to predict the product for this one. And yes, by the way, the left side of my brain one, this is found in the body. And we actually use this to create a type of what we call complex saponifiable lipid. This is found in phospholipids, for example, the membranes that make up the the covering of all cells, for example. So, yeah. Okay, so let's move on. Here we have another example of these phosphate bridges. They're already dissolved in water, so that you don't see their hydrogens present. But here we can see this looks very similar to the carboxylic anhydride, where imagine 2 phosphates. They actually formed a nice bridge. Notice we have 3 phosphates. So when we have 3 phosphates right here, we would call this cleverly a triphosphate. A triphosphate. So yes, you can see where I'm going with this. This is the high-powered center of ATP. Adenosine, and adenosine is this big ugly monstrosity molecule to the right. That's adenosine. And then the rest of this, and I'll use my highlighter, the rest of this is going to be triphosphate. Now, the body needs to have these very quick molecules it can dispatch to all parts of the body, all different cells, to power up its various chemical reactions. So these are these fast-moving molecular batteries, if you will. And what happens is, when we eat food, we actually, the end product, no pun intended, so to speak, is to go ahead and perform an inorganic esterification, where we actually stick this phosphate onto these other phosphates, and we go from a diphosphate, to a triphosphate. It takes a lot of energy to put it on. So the minute these molecular batteries are used and injected to power a chemical reaction, then bam, this will fly off and it will release a whole bunch of energy used to power various chemical processes. And it goes from ATP to ADP. If we go to the next slide right here, here we see the reaction. It uses a nearby solvent, water molecule, to start this reaction when this phosphate is actually broken. So you can think of this as a hydrolysis reaction. We go from ATP to ADP. You can notice there's a diphosphate. So here we have our inorganic anhydride, if you want to be technical about it. ATP to ADP, 2 phosphates. And as a phosphate leaves, it releases a whole bunch of energy. You're responsible for this overall process. I could ask you to give me a quick summary on this. I am not going to ask you to sketch the products, at least not yet. But you are expected to know the names as well as the general theory of what's happening here. And that concludes these slides.